Hello students, today we are going to talk something very extensive about the emission, photoelectric emission, and then we shall also study the behavior of photoelectric current, variation in photoelectric current with the various factors dictating it. So let us start now. What is photoelectricity? We have already discussed that whenever a light having frequency equal to or above a particular frequency for a given material metal, that frequency particular frequency is known as cutoff frequency, and if the light is having frequency equal to that and above that frequency, cutoff frequency, also called threshold frequency, then the light is being absorbed by the electrons of the metal, and then they are energetic enough to jump away from the metallic surface, break away the grip of atoms of the metal, and these electrons are known as photoelectrons, and the current produced due to these electrons is known as photoelectric current or photoelectricity. Now experimental arrangement is made according to this. This is one typical way of producing it. What we do is we have a partially evacuated vacuum chamber, which is also known as discharge tube, and we are having a window having a cover of quartz so that light can enter through it, but the electrons cannot pressure inside the discharge tube is maintained. And then when the light ray is allowed to fall on a metal plate placed at point C, this is the metal plate receives the light having frequency above or equal to the cutoff frequency, and this metal plate starts releasing photoelectrons. If we keep a plate over here which is positively charged, then it will naturally attract those electrons, and as the electrons are received by this plate, which is also known as collector plate, it is usually kept at positive terminal or connected to the positive terminal of the plate, and so the electrons received over here passes through the ammeter, and therefore the photoelectric current can be measured. So this device measures the I photo. And the voltage applied across this collecting plate will be measured by this voltmeter. This gives us voltage V across the plate applied by this battery, and we use a rheostat to vary the potential of this collecting plate. It can be made positive, it can be made negative, depending whether it is on the right half part of the rheostat or the left half part of the rheostat. So now once we have understood how the photoelectric emission is taking place and how we are in a position to study the variations in photoelectric current with variation in various factors, now it is very much obvious the photoelectric equation is given by Einstein is E is equal to h nu plus half mv max square. We have already discussed this, and E is equal to h nu, the incident energy, equal to the threshold energy plus the maximum kinetic energy possessed by the photoelectrons. Now if we do some variation in the potential of the collector plate, and instead of keeping it positive, if we start giving it negative potential, gradually decreasing from positive to zero potential, and then finally making it negative by use of this commutator, we can reverse the direction of potential applied, or we can also slide it on to vary the potential, slide it on the rheostat. So that means now here you see we can vary the polarity of the collecting plate by changing the plug of the commutator. So if we vary this potential from positive to some negative value, and gradually increasing the negative value, what will happen? The electrons, those which were being attracted by the collector plate, are no longer attracting, it is repelling, it starts repelling those electrons which were reaching the collector plate. And there could be a particular negative potential of this collector plate for which no electron is able to reach the plate. Why this happens? Because whatever the kinetic energy electrons which were photoelectrons which were emitted by the metal plate, if that maximum kinetic energy of those electrons becomes equal to the potential energy of this point, then those electrons are just able to reach the plate, and before at connecting the plate it is forced to return back due to negative potential of this plate. And that potential for which no current flows through the collector plate is known as cutoff voltage. And for that situation we will have a relation, the net incident energy h nu minus the threshold energy. So remaining energy is given in the form of kinetic energy to the photoelectrons, and maximum kinetic energy, if that maximum kinetic energy becomes equal to electric potential energy of this due to this negative potential of the collector plate, then in that case no electron will be able to reach point A. So we will have this equation for that situation. Now we consider various variations and draw the graph related to those variations. Let us talk about the first variation for variable intensity and constant frequency. We are keeping the intensity varying while keeping the frequency same, and then the collector plate voltage versus photoelectric current. We plot this graph. What we see that the cutoff frequency will remain same, because the cutoff frequency, you see, will depend on the frequency of the incident minus the threshold frequency, the threshold energy. So that means it depends upon the frequency, therefore the cutoff frequency remains same, whether the intensity is high, whether the intensity is low. One thing you can understand, if the intensity is high, then in that case what happens, the number of photoelectrons emitted will be large, but the maximum kinetic energy carried by any electron will be always same. It will depend only on the frequency, and therefore the maximum kinetic energy for a given frequency is always same. For a given material, for a given metal, for a given incident frequency, we have the maximum kinetic energy fixed, and that for given fixed kinetic energy, the cutoff potential will also be fixed, because charge on electron is always constant. And so here we have the current photocurrent versus potential graph. We have different curves starting from the same cutoff voltage, but the saturation current means when the current anode, the current collected passing through the collector plate becomes constant or saturates, that is known as saturation current. And how this happens, if we keep on increasing the if we keep on increasing the potential of plate A, what happens, the electrons which were emitted, photoelectrons, are getting collected mostly by the plate, and finally all the electrons at some stage will be collected by the plate. Now once you have collected all the electrons emitted, so no longer there is a scope of increase in current, and therefore whether you increase the voltage by some amount, you increase the collector plate voltage, still the number of electrons reaching the collector plate will remain constant, unchanged, and therefore current will also remain unchanged. So after saturation current is achieved, if you further increase the voltage, still there is no change in current, and therefore that current is known as saturation current. So here you see the saturation current is different for different intensities, but the cutoff voltage for all these are same, because that depends only upon the frequency, incident frequency for a given material. Now second, we talk about graph for intensity of light versus photocurrent, saturation photocurrent. For a given intensity, when you increase the intensity, the saturation current increases linearly. Saturation current means this part of the current is depicted here. So when the intensity is increased, the saturation current also increases, keeping the frequency constant. Here also you see that for a given frequency, the intensity is for a given intensity, the saturation current is given there. For the lowest intensity, the saturation current is lowest, and for the highest intensity, the saturation current is highest, and therefore this is having a linear relationship. That means saturation photocurrent is always proportional to the incident intensity, keeping the frequency constant. Now we talk about the third graph for different photocurrent versus potential, collector plate potential, when intensity is kept constant and frequency is varied. When the intensity is constant, you see the saturation current will be fixed. But if we are varying the frequency, and since frequency decides the cutoff voltage, therefore for different frequencies we have different cutoff voltage, but since the intensities of all these are same, therefore the saturation current will always remain same, but the cutoff voltage for different frequencies will be different. So this is the third graph, and fourth graph we study is collector potential current for photoelectric current versus collector plate potential for having different intensities and different frequency. Here we have kept the intensity same, but the frequencies are varied. Now here we are varying the intensity as well as the frequencies, and for our convenience we are taking that while I3 is the greatest intensity and I1 is the smallest one, lower one is representing nu1 and I1, and the top one is representing nu3 and I3. This is having the highest frequency as well as highest intensity. Since the frequency is highest, therefore the cutoff voltage will be highest, and since the intensity is highest, therefore the saturation current will be highest. And for this case, first case, the frequency is lowest, and therefore the cutoff voltage will be lowest, and since the intensity is also lowest, therefore the saturation current will be also lowest. So I hope that you have understood it. These are very tricky situations. You must go through it more than once, so that it is well absorbed by you and understood by you. Thank you and have a nice day.